And I will present a new method to detect convergent weight shifts for non-coding regions on phylogenetic trees. And so the motivation of our new tool is to identify regulatory regions associated with phenotypic convergence. Here are three examples of phenotypic convergence. Loss of blindness in birds, and in pythons and boas they evolve into similar trees, and transitions to ocean life in mammals. Current method to detect convergent rate shifts, including phylo-P in the FAST program. Phylo-P compares the likelihood under two models. In the null model, they assume only one rate across all the branches, and in the alternative model, they assume a different rate in a group of branches than the rest of the branch. And however, phylo-P limit to test only a single predefined patterns of rate shifts. Also, it failed to distinguish a single strong acceleration in one target class and weaker acceleration in multiple classes. Here is an example. These three elements have different acceleration patterns. However, they have the same likelihood ratio. In the first element, it only accelerates in one target species. I forgot to mention, the red branch means higher substitution rate, and the green branches means lower substitution rate. And the middle element has multiple accelerations in all the target species. The third element has accelerations in both target and non-target species. The first two elements should be selected as target-specific accelerated elements and may be associated with the loss of function in target species. However, the third one should be excluded as it may indicate a broader function. The middle one is more interesting, is more likely to associate with phenotype convergence as it shows convergence shifts of substitution rate. Our method can distinguish these three elements and will select the first two elements. Here is the overview of our method. The input is a phylogenetic tree, and the branch length is estimated from the neutral background sequence, and also another input is the sequence alignment. The output is a phylogenetic tree with the substitution rate shift patterns. Here, the color indicates the shift of substitution rate. And we will also output two scores, two base factors, to show how strongly this element, the sequence of this element is associated with the phenotype change. The model of substitution rate change is similar to the local random clock model in BEAST. Well, we assume there are three types of latent state on each branch. The background state or neutral state, and the conserved state, and the accelerated state. And these three states have different substitution rates. And in the background state, the substitution rate is 1 relative to the background sequence. And for the conserved state, the substitution rate is smaller than 1. And for the accelerated rate, the substitution rate is higher than in the conserved state. For a typical element, it may be at neutral background state at the root, and then gain conservation in one or more clades, and then lost conservation in multiple lineages. And we model the transition of latent state Z by a Markov process, and we use MCMC to do the inference. And then we test the parallel acceleration in target species, and we compare three nested models and to test which model fits our data sequence data best. First, the null model. In the null model, we allow no accelerations across all the branches. And in the lineage-specific model, M1, we only allow acceleration happen on the branch leading to the target species. In the full model, M2, we don't have any constraint on the latent states besides the dollars in reversibility, which element, once it lost conservation, it cannot regain conservation. And we compute the base factors between M1 and M0. This base factor is mainly to identify the elements that shows acceleration in target species. We also compute another base factor between M1, which is marginal likelihood between M1 and M2, and this Bayes vector is used to exclude those elements that shows acceleration in non-target species. Or if an element has acceleration in non-target species, it will fit M2 better, so the log BF2 will be smaller. We did some simulation study based on the example of loss of light in red hats. Here is a simplified version of our bird phylogeny, and there are 3 to 5 losses of lightness in red hats. So we simulate different acceleration patterns and mix them with the elements with no acceleration, and test if our method can identify the elements with acceleration in red hats. And here is an ROC curve. We compare our method with phylo P and other methods, and our method is better than phylo P and other methods in all the scenarios. And then we want to show we compare our method with least 2 to show if our methods can recover the true patterns of substitution rate change. And in the simpler scenario where only one clade accelerated, our method is similar to beast 2. Here, the x-axis is the ratio between accelerated rate and conserved rate, and the y-axis is the accuracy. So, and then for more complex case with multiple accelerated clades, our method performs better than beast 2. For the real data, we apply our method to 280,000 CNEs, conserved non-axiomic elements, and we identified about 2,000 red hat-specific accelerated elements. Here are 3 examples. They have different acceleration patterns. For details of the biological function of these elements, please read this paper. And we also apply our method to mammalian genome. And here is a simplified version of the mammalian phylogeny. And there are 3 independent invasions to the ocean habitats in mammals. And we use whole genome alignment of 62 mammalian species and identify 280,000 CNEs. And then we apply our method to these CNEs and identify around 2,000 mammalian-specific accelerated elements. And then we find the genes near to those CNEs, those noncoding regions, to see if these genes have similar function. We did gene set enrichment analysis for these genes, and they enriched in gene ontology terms related to nervous and immune systems, and also they also show enrichment in the phenotype terms associated with the morphological traits. And this has not been identified in the protein coding sequence in previous studies. And then we extend our methods to allow for different gene tree variation. And due to incomplete lineage sorting, each element can have different gene topology, and also the branch length can be different for each element due to coalescence process. And so given a species tree and the effective sample and the population size parameters, we use we use multi-species coalescence model as the prior for our gene trees, and then we test the correlation between the sequence rate shifts and the phenotypes, accounting for the phylogenetic uncertainty. And the tree space is very large, so it's hard to, because we want to compute the Bayes vector, we have to integrate out all the configurations of the trees. It's very hard to compute the Bayes vectors, so we have a new method to compute the Bayes vectors, including the gene tree identity based on MCMC samples. And then we did some simulation study. So we simulate element with no acceleration, and here is the result. The x-axis is the species, and the y-axis is the probability of each branch, the posterior probability on each branch. So for this simulation study, we want to test if our method can recover the true substitution rate change. And we compare the model with fixed tree and the model with a variable tree. And the yellow bar shows the results with fixed tree, and the blue bar is the result for variable gene tree. And so from these results, it shows that the model with variable tree has better performance estimating, detecting the grid shifts than the fixed tree model. And the result is similar for the simulation with convergent estimation in red hats. And then we compare these two models and to see how well they can estimate the substitution rate. It's not surprising. The model with variable tree can better estimate the substitution rate than the model with fixed tree. So the top figures shows the estimate accelerate rate in respect of the true accelerate rate. And the top two figures is the estimate conserved rate in respect of the true conserved rate. Especially for estimating accelerate rate, models with variable tree is better. And also when modeling gene tree variation, the null space is larger. So the likelihood from the null model is larger. The log base factor 1 is smaller, so it's more conservative to identify acceleration for the variable gene tree model. In summary, convergence can be a powerful means to identify the function of non-coding elements. And we developed a new method called phylogenetic, which can detect genomic regions with convergent redshifts correlate with convergent phenotype changes. We can also reconstruct a complex pattern of substitution rate for each element. And this method can also be used to discover normal function groups by clustering genomic regions with similar evolutionary patterns. Finally, I will thank my advisors, Scott and Jin Liu from Statistics Department, and also my collaborators. And thank you for your attention.